My name is Kelly Praskovich. I'm our Director of Alumni Relations here in the Eberly College of Science. Thank you for joining us today for the webinar. We're excited for you to engage, learn, and ask us questions. This is the first webinar in a series, so keep watching. Today's webinar is Little Red Dots Beyond the Milky Way. Our presenter is Dr. Joe Leja. He holds the Dr. Keiko Meanwhile-Ross Endowed Early Career Chair and is Assistant Professor of Astronomy and Astrophysics here at Penn State. Joel, thank you so much for sharing your time with us today.
Lovely. Well, thank you very much for the introduction, Kelly, and thank you everyone for coming out today on this Tuesday afternoon. This is a fantastic turnout. So I'm going to go ahead and get started here, and we'll start. I'm going to have Webb launching in the background. This is just a video of the rocket launch from French Guiana, putting the James Webb Space Telescope into space. So a fantastic moment.
Tropical rainforest to the edge of time itself, James Webb begins a voyage back to the birth of the universe.
Okay.
Punching a hole through the clouds.
This is a grandiose language, and I think it's fully appropriate. The James Webb Space Telescope, I'm going to give an overview of one of the most exciting mysteries, maybe the most exciting mystery, uncovered by the James Webb Space Telescope. And for people like me, this telescope, it's a huge deal. It's like the pyramids or the first landing on the moon. It's a wonder of the modern world. So you only get to discover the early universe one time, and we're doing it right now. So strap in and let me tell you about it. I'm going to take you through our exploration to the edge of the universe, and we'll discuss the incredible mystery of these little red dots that James Webb has uncovered. These are by far the coolest and most perplexing objects I've ever seen. And so much of this has been in the news already, but I'll also show you some things that aren't in the news yet. So in short, there is a lot going on. So we will be looking through Webb's infrared eyes, and by the end of the presentation, I will take you to the very edge of the universe. But we'll start a little bit closer to home. So this is midnight at Cherry Springs Park, Pennsylvania, just a couple hours from here at Penn State. One of the darkest sky sites in the eastern U.S. And so here I'm just going to highlight something you can see. When the sun sets, you can see the galaxy come out. This is the Milky Way. What a glorious sight it is. This is approximately what it looks like to the naked eye. Maybe some of you have seen it. And there's a lot of beautiful things to see here. It's a fantastic sight, but I want to focus somewhere special. The galactic center, the center of the galaxy, right here. You can see it. It's right up there in the sky. It's something like 26,000 light years away. And so, just to put that into context, if you traveled at the speed of light for all of recorded human history, before your grandparents, 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 and so on lived, you would only be a fraction of the way there. And this is the closest place we'll be visiting in this talk. This is effectively our backyard. Let's go ahead and head there, to the galactic center. We'll take a little movie and zoom right in. This is courtesy of ESA, the European Southern Observatory. And we can go there if you're feeling brave. We'll go right to the center. This is an exotic place. It's actually pretty much invisible to the human eye because of the huge amounts of gas and dust between us and the galactic center. It obscures our vision. Something like 1 in 10 billion photons will make it. But we astronomers have infrared eyes, and infrared eyes can see right to the heart of the Milky Way, like this. And here we are. This is the center of the galaxy, 26,000 light years away. This is an incredible place. It's very strange, actually. It's very exotic. This is something called the nuclear stellar disk. It's a billion stars in a very, very tiny volume. It's incredibly dense, something like 500 times denser than our local sky. And so on average, the nearest star is 1/10 of a light year away, something like 40 times closer than our nearest star. And there's no real rest. The night sky is very bright here. It's so packed with stars. And most of these stars are also ancient. They formed more than 10 billion years ago, a very long time ago. So this is an exotic place, but we're actually not stopping here. We're going a little bit closer in. towards something called Sagittarius A star. And this is what we're going to focus on first. Uh, This is at the very heart of the Milky Way. It's an exotic place. And so what I'm going to show you actually is the first image of this so-called supermassive black hole at the heart of the Milky Way. This thing is huge. It's so massive that light can't escape, but it's not a normal black hole. It is something like 4 million suns worth of black hole. It is massive. And keep in mind, the sun is about 300,000 Earths, so this thing is huge. It sits right at the heart of our Milky Way. This is the first image we have of this black hole. We don't actually see the black hole itself, which is here in the center. Instead, we see this ring of hot gas around the black hole, which is falling into the black hole and getting superheated. This is the first, one of the first times an event horizon has ever been imaged. So this is a very special image, actually, from just a couple years ago. So this is the emission ring I was talking about. And just to give you a sense of scale for this massive black hole, this is approximately the orbit of Mercury. So this thing is huge, and it lives at the heart of our galaxy. And you might wonder, does that make it special? Is this unusual? Is this normal? Can we put this into context? Well, I told you this is the closest place we'll be going today. So enough with our backyard. Let's go somewhere exciting. Let's go somewhere different. We're actually going to go right over here in Virgo, and we're going to go to a special object in Virgo, in the Virgo constellation, a galaxy called M87. So this is a giant elliptical galaxy, and it's a very special place, actually. It is one of the most massive galaxies nearby. We're now looking something like 53 million light years from Earth. And the stars in this galaxy weigh as much as about 400 billion suns, or about 10 times the size of the Milky Way. This is a very unusual system. Here's a little picture of it, and you see a little radio jet being shot out from the center. And the center of this galaxy is also unusual. It's even more exotic, something like 5 times more dense with stars than the Milky Way center. So if you had trouble sleeping at night in the center of the Milky Way, you would never sleep here. It would be incredibly bright. And we can zoom in even farther. This here, the black hole at the heart of M87, this was imaged in 2017 by the Event Horizon Telescope. It is the first event horizon of a black hole we have ever seen. And this black hole, remember the Milky Way's black hole had a mass of 4 million suns. This one has 6.5 billion suns worth of mass here. It is incredible. It is strange. Here it is. Here's the first picture of it. You see the black hole in the center and the superheated hot gas emission ring around it. And just for context, let me show you here. This is Pluto's orbit. This thing is huge. This is bigger than our solar system. All right, and one last thing for context here. This is Voyager 1, or where it would be if we launched it from the center of the black hole. Voyager 1 has traveled for something like 50 years and is the most distant man-made object. So just for scale, this thing is gargantuan. All right. So what's going on? Why do the centers of galaxies have these supermassive black holes? Is this normal? Does every galaxy look like this? So we've mapped this exhaustively at this point, and I'll show you a little plot here. This is one of the few plots I'll show in this talk. But here I'm showing, this is a survey of galaxies in the nearby universe. The x-axis is how many stars live in the center of that galaxy, and the y-axis is how big is the central black hole in that galaxy. This is all of our nearby galaxies. And you can see pretty much every single galaxy has one of these supermassive black holes. They are huge. They all live in the center. And bizarrely, the bigger the galaxy, the bigger the black hole. You can see the Milky Way here. It's near the lower left. It's one of the more normal galaxies in this plot. Some of these black holes are gargantuan. But the big question here is why? Why did the universe do this? Why does every galaxy have one of these supermassive black holes at the center? We can establish this as a fact observationally. We can see the black holes, we can see the galaxies. But what that won't tell us is why the universe chooses to form these objects like this. It's an incredible puzzle, actually, and one of the great puzzles in astrophysics. What's going on? We've kind of divided this into three different scenarios. But the idea is that these supermassive black holes and their galaxies, they have to grow up together. They go to kindergarten together, they go through middle school together, they graduate high school together, college maybe, they get married, they live their lives together. That much we know, but we don't quite know how it happens yet, or why it happens. And so the idea is there's kind of three different ways we can think about this problem. We start at the early universe, right after the Big Bang maybe, and we come up to today. And so these things could grow together. Maybe they do grow at the same time and they grow up with each other, something we call symbiosis. So the galaxy grows, the black hole grows, everything grows together. It doesn't answer why those things are there, but we form a galaxy at the same rate as we form a black hole. That's one possibility. Another possibility, something called dominance, the dominance scenario here, where this supermassive black hole, through some exotic physics, through some unknown physics, something we don't understand yet, formed at the beginning of the universe, near the beginning of time, and we'll come back to this later, and then the galaxy grew up around it. The dominance scenario, quite possible. And then a third possibility, something called the adjustment scenario, where these galaxies full of stars, things like the Milky Way, with planets like Earth, well, they formed first, and then these black holes, they came around later through some other mechanism. They popped up, and they must have grown quite rapidly to catch up. Something like this is going on. But we can't actually tell what's going on from here in the local universe. All the action has already happened. Luckily, physics to the rescue. The universe itself is actually so big that it takes light a very long time to cross it. This is a huge advantage for astronomers. So we see distant objects not as they are today, but as they were in the past. And this also appears redder. These objects, they appear redder because the light is stretched by the expansion of the universe. So if we can look at very distant objects in the near infrared or the far infrared, we go deeper into red light, we can see these objects as they were at earlier times. And we can try to figure out what came first, the supermassive black hole or the galaxy. This is a fantastic opportunity afforded us by the universe. And to exploit this, we built the James Webb Space Telescope. And so this is a fantastic piece of technology. It's a massive undertaking. Like I said, it's something like the modern day equivalent of the pyramids. It's a wonder of the world. It's the first time we built any telescope like this. It had to self-assemble in space. All the telescope engineers who built it were terrified. There were something like 250 so-called single-point failures. If anything failed, James Webb would have been a failure itself, which would be a complete tragedy. I mean, this thing cost $10 billion. It took 25 years to build. It's the most expensive telescope ever built. It orbits the sun. It's not near the Earth, so if something went wrong, we would never be able to fix it. But luckily, you saw the launch. You would have seen in the news if something bad happened. James Webb is working fantastically, and it can answer the questions it was built to answer. It can peer deep enough into the universe to glimpse the first few 100 million years after the Big Bang. Basically, if anything is bright enough to see after the great cosmic fog is burned off, we'll be able to see it. Okay? That's what we built James Webb to do, and nothing else is going to uncover the first stars, the first galaxies like James Webb can. It's built explicitly for this. And so this is just a fantastic opportunity. It's super exciting. All of my colleagues and I were just riveted to our screens as soon as it went up. James Webb was able to answer very, very quickly some of the biggest questions we have about the universe. Things like, how and when did the first stars, the first galaxies, and the first black holes form? And maybe most crucially, the questions we did not think to ask. What mysteries is the universe hiding that we haven't even thought of yet? So these giant space telescopes built by NASA and space agencies around the world, they're kind of like ships of discovery. We're sailing into the unknown, and we don't know what awaits us there. And so we know from the Hubble Space Telescope, if you wrote down the 10 questions Hubble was supposed to answer, and then you compare it to Hubble's 10 biggest discoveries, there's almost no items that are in both of these lists. So the most exciting questions are often the ones we didn't think to ask. This is the last image of James Webb as it sailed off into deep space. It's the last picture we have. And so this is just a little quote from author Nadia Drake about the similar moments for the Hubble Space Telescope when it first went up and the first things it saw. And so one of the first things they wanted to do with the Hubble Space Telescope is point at this blank patch of sky for a long time and see what came out. And so I'll just read the quote because I think it's amazing. So in 1995, astronomer Bob Williams wanted to point the Hubble Space Telescope at a patch of sky filled with absolutely nothing remarkable for 100 hours. It was a terrible idea, his colleagues told him, and a waste of valuable telescope time. People would kill for that amount of time with the sharpest tool in the shed, they said, and besides, no way would the distant galaxies Williams hoped to see be bright enough for Hubble to uncover. That turned out to be completely wrong. And this proposal, staring for 100 hours at a blank patch of sky, this turned into something called the Hubble Deep Field, probably the single most influential image in astronomy. And so when Webb went up, we didn't wait. Webb started taking these deep fields immediately. And so I'll take you to one of them. This is the Sculptor constellation. And here I've just highlighted a tiny, tiny, tiny patch of the sky. You could go outside on a night sky and stare up at it yourself. This is one of the first Webb deep fields, the Uncover field. This is one that my team actually led the analysis of. And so when Webb went up, this happened pretty much immediately. This is it. This is something like 60 hours of Webb time, something like 2.5 days. This is an incredible deep field. Almost every point of light in this field is a distant galaxy, seen at some different time in the universe. Some of these are basically our cosmic neighbors. And I can tell you, there are a couple of objects that come from just a couple of 100 million years after the Big Bang in this picture. Some of the most distant objects ever seen by humans. Okay. So this was just an incredible opportunity, hundreds of thousands of galaxies. And so my colleagues and I were sifting through all of them to find ones that might be from the early universe. Maybe 1 in 1,000, we get lucky. The special ones will look like these faint little red dots. Let me show you one of them. So 5 days after the first Webb data were released, this was July 2022, we found the most distant galaxy that had ever been seen. Here it is, Glass C12. It looks like a little red dot, but this is not the little red dots I'm going to tell you about. I'll tell you about those in a second. And this is an early universe galaxy. And so all of these data were public immediately, and this just produced an absolute flurry of activity. Fundamental questions about how galaxies form, how they evolved, that were unanswerable a week before, could suddenly be answered by anyone with the right expertise. Just a few tens of hours looking at these images. Okay? So Webb immediately broke the record for the most distant object, and it continued to break it again and again and again and again. It's an incredible instrument. In fall 2023, not that much longer, we actually found some of these very distant objects ourselves here at Penn State. One of the postdocs working with me, Dr. Bingji Wang, she found the second and the fourth most distant objects ever seen by humans. It's Wikipedia confirmed. You can go check it out there. But this was Uncover Z12 and Uncover Z13. Here I'm just showing a couple pictures of them. These are entire galaxies that existed only 330 million years after the Big Bang. And something I'm going to tell you about in this talk quite a bit is how surprising it was to find galaxies so early. 330 million years after the Big Bang might sound like a long time, but this is something like 3% the age of the universe, 2% the age of the universe. We thought maybe the universe would have cooled to form the first stars by this point, but instead we're finding galaxies full of stars. They're far brighter and they're far earlier than our models predicted. So there's a real mystery here that we're still struggling to understand. And why are galaxies forming so early and so quickly? The current record holder, this came out almost exactly a month ago. And we discovered this thing. It's called MOM, which stands for Mirage or Miracle. It's the name of the survey that found it. It's not a mom. But they call it MOM Z14. And so this object, this is currently the most distant object known to humans. It's lived for about 200, it's about 280 million years after the Big Bang. So this is incredible. Sharks have been on Earth for longer than this. 280 million years after the Big Bang. This was very close to the beginning of time. And I can tell you right now, we've already observed things like carbon and nitrogen in this early system. This elemental analysis was actually led here at Penn State by my grad student, Eberly. So we understand that this is not the first generation of stars, which should have formed out of this almost primordial hydrogen and helium. But the abundance, the analysis of this galaxy suggests it's only been a couple generations of stars. We're really seeing very close to the beginning of time here. This was shocking. Like I said, too early, too bright. So we're finding these first galaxies very soon. What other surprises might be lurking at the edge of the universe, the observable universe? How do we explain this? And now I'll tell you about these little red dots. Not the galaxies I'm showing here, but something else. So this popped out of Webb's data almost immediately. Webb's first month revealed these early universe objects, which appeared to be these incredibly bright, incredibly massive galaxies. And so they were called universe breakers by our team because they really broke our conception of what we were expecting to find in the early universe. Here's 7 of them. Hey, this literally came out of Webb's first month. We wrote this Nature paper in like 4 days. It was incredibly fast. Just to put this in context, here's a little plot. This is just showing all of the objects in one of these first deep fields. On the y-axis is the logarithm of how much these objects weigh, and on the x-axis is how far away they are. You don't need to understand any of the numbers. Let me just annotate this dashed line. This is the mass of our own Milky Way, which took, 14 billion years to grow. And this is the age of the universe when it was 500 million years old, 3% of the current age. And so these things appear to be huge, and they're very, very early. This is truly shocking to people like me. It's like checking in on your newborn and finding a fully grown adult. You have big questions. And so we figured there was something wrong with this, maybe many things wrong. So, of course, it went right to Nature, and it had a huge impact. There was a ton of press that came from this discovery, and actually rightfully so. These little red dots are huge mysteries. This was a massive deal. It was one of the stories of the year for 2023, maybe the science story of the year. So this was an incredible discovery. One of these little pictures is an interview. I got to go on live TV, which was a very exciting experience. I found out how this worked. They let me ask questions of myself ahead of time. I would write down questions for them to ask. And so I went on live TV and they started asking me questions, and I think they must have gotten distracted halfway through, because halfway through there was a pivot. They went off script and said, so let's talk about something else. Aliens? Are they real? You got to be careful with live TV. By the way, Webb has not discovered aliens, though there are also very exciting, tantalizing hints about planets, the atmospheres of other planets. Anyway, that's a different topic for another day. Hey, this was a huge deal, these little red dots. So what are they? Are they massive galaxies like we thought? Well, there were a flurry of studies that happened afterwards. Whatever they are, they're everywhere. Okay, there's a reason we saw them immediately when the first Webb images came out. They're all over the sky. Actually, if you go outside tonight and look up at the sky, there's probably something like 10 million little red dots staring back at you. That's our estimate right now. 10 million, just glowing there in the night sky. A shockingly common object for us to have never seen them before. The other thing we know, this is unique to the early universe. We stopped making them after 2 or 3 billion years. We don't make these anymore. There's something very special near the beginning of time. Little red dots. So we kind of narrowed it down to one of the following things. One, our models for understanding how galaxies formed are very wrong, super wrong, in some fundamental way. There's a dozen ways it could be wrong. Two, our understanding of the universe itself, cosmology, is flawed. We need new physics. Okay, structures should not form in the universe this quickly. Or the third possibility, these little red dots, they're no galaxies at all. Instead, they're these huge, supermassive, feeding black holes, like we talked about at the beginning, stuff like at the heart of the Milky Way. What would that mean? Well, we talked about this a bit. Supermassive black holes, every galaxy has one, lives at the heart. We see these black holes light up when they eat things like gas and stars. They get very bright, very hot. Normally, in a normal galaxy like the Milky Way, these black holes are something like 1/300th the mass of the galaxy they live in. And so if these little red dots are powered by supermassive black holes, these supermassive black holes would themselves be huge. They wouldn't be 1/300th the mass of the galaxy. They would be 10% the mass of the galaxy, or even 100% the mass of the galaxy. And these black holes, they would be something like 100 times larger than our own Milky Way's black hole. They are huge. And so this other explanation isn't that comforting. Actually, it's its own problem. Hey, we now need to create these supermassive black holes very early. Preposterous. This is just as confusing, just as exotic, and just as strange as them being massive galaxies. So how did they get so big at the beginning of time? Were they born that way? Why? How? Lots of questions, not very many answers. And so we needed more data, and we have it at this point. A year ago, we pointed the James Webb Space Telescope for much longer at some of the brightest and the most distant little red dots. This is when the universe was 700, 800 million years old. And the data that came back were very surprising. We had these two different theories for what might be going on. Either these very massive, very tiny galaxies, or these very bright black holes, supermassive black holes. And so our first data, our longer data here, this is right off of the Webb telescope. This is a spectrum and a picture of one of those little objects. And I'll just show you what we saw. And we saw two things. One, we see gas spinning around, something at thousands of miles per second, orbiting this black hole. And we also saw another signature, very unique, cold, dense hydrogen gas, a lot of it. And this normally means the atmospheres of stars, and not just the atmosphere of any star, the atmosphere of old stars, very red stars. So our two hypotheses for what seemed to be going on, it seemed like both were true at once. What the heck? A real curveball. This was about a year ago. This was also led by Dr. Bingji Wang here at Penn State. So this was shocking to us. The most straightforward interpretation was that both things were happening. These are tiny, very dense galaxies, and they seem to have co-formed with their supermassive black holes. A suggestion for how these supermassive black holes might have come to be. But it all happened right after the universe began, way sooner than anyone expected. I can't emphasize how exotic or strange this is. I don't think I can do it words. But it's something like taking the entire Milky Way, this thing that's splayed out across the entire sky, crushing it down into a sphere 100 times smaller, and then throwing this actively feasting supermassive black hole right in the center. It would be just next door. It would be closer than Betelgeuse. It would be closer than most of the stars we see in the night sky. So we'd be taking something like this. This is a picture of Andromeda, but here I'm just going to squeeze it all the way down to something that would look like a little red dot. Boop! That's small. And then we'd stick a supermassive black hole in the center, just blasting out material, incredibly bright. This is insane, even for astrophysicists. All sorts of crazy things would be happening in a system like this. Stars would be running into each other like once a week. That would also light up the night sky. It would just be incredibly exotic. So this really flummoxed the entire community, I think. And there's been other explanations for these objects, probably at least one per week. But all of them are pretty much equally exotic, or even weirder. Hey, so some of the things that are coming out, this has just entranced the astrophysical community. Maybe there's no black holes at all. People are thinking maybe instead there's so many stars that everything moves as fast as it does near a black hole. It simulates a black hole. Another possibility, maybe there's no stars at all. Instead, we have this humongous black hole, and it's eating gas so quickly that it looks like it has this fast-moving atmosphere. But all of that gas is actually being sucked into the black hole, and it's very cold and dense and just flowing right in, like the atmosphere of the Earth collapsing on itself. Completely wild. These explanations seem strange, but it turns out this last one might have some merit. And now we're getting close to the present. Hey, this was January 2025. I went home for Christmas break. I had a great time. Hey, but the James Webb Space Telescope was hard at work. There were two separate international teams. Our group was on both. And we found these two unique little red dots, which had these features which kind of ruled out a lot of the possibilities. Hey, and this was awesome. This was a huge find. And we found two at once, so it wasn't a fluke. This came out in the last couple months. This is the title of one of the papers submitted to Nature, and it was dubbed a black hole star, which I think it's a poor name. I'll be honest with you. But the idea is it is a supermassive black hole with this huge atmospheric river of gas, probably flowing inwards. Okay, it's eating this gas very, very quickly. And it's happening near the beginning of time. This is remarkable for a number of reasons. Okay? But it's a huge breakthrough in these studies, and it's the only theory that seems to fit the data so far. So we have this massive, thick, basically an atmosphere. It's not really a star, it's a bad name, but it's a thick atmosphere of gas, and it's very cool, it's very dense, and it seems to be flowing like a river into the heart of these black holes. Very strange. Not what I expected. Not on my bingo card. This could solve the biggest mystery from James Webb so far. And I say could because these objects are so strange and they've given us so many surprises. I'm not ready to declare victory yet. But it also presents new questions. How did these supermassive black holes form so big, so early? Why is there all this dense hydrogen gas around them? And why are they everywhere in the universe? And why did they then disappear? One last clue. Came out last month. James Webb has a very special mode, high resolution spectroscopy. It's extremely expensive, but these little red dots merited this cost. And it found something very interesting, a clue. The gas surrounding one of these little red dots, it's a very special little red dot for a number of reasons. But it appears to have something like less than 1% the abundance of heavy elements, stuff that you and I are made out of, carbon, nitrogen, oxygen, that we have today. So it's nearly pristine gas. This is nearly from the Big Bang itself. This is weird. This is actually very weird. This is a very crucial piece of the puzzle. Why? Supermassive black holes, they should grow over billions of years, a very long time, by eating gas. And this gas is usually, it forms new stars. New stars form heavy elements. Those heavy elements pollute the gas around them. And so it's a cycle. All of this happens at once. But if the gas is pristine, they couldn't have grown this way. The black holes had to grow some other way. They can't grow by eating gas. They had to start out big. What does that mean? What then? How did they form? What incredible physics can create these huge black holes so early from near pristine gas without any stars? There's two possibilities if these observations are right. And one is the exotic deaths of the first stars. These first stars are very special. They're formed only from hydrogen and helium, so they have a very special composition. They probably work unlike any other star that we have. They would collapse directly into these supermassive black holes. Shocking. But the other possibility, and this one's almost more favored by the data, and very tentative, very early. Okay. But this is the other possibility. It could be some unknown physics that produce huge primordial black holes. And so these wouldn't come from stars like the other black holes that we know of. This would be formed through some exotic process in the first few minutes of the universe, these so-called primordial black holes. So we don't know which of these is happening, but the fact that they're so big so early and there are no heavy elements around them, it's very hard to explain any other way. Okay. So how do we test it? This is science, right? We can still test things. Well, if black holes form first, the dominant scenario, and then galaxies form around them, if we look at these very bright, very early galaxies, we should see overmassive black holes. They should be very common. And so, upcoming James Webb's observations. This is led by Dr. Jake Helton, who will be joining Penn State soon. He's the Evolving Universe postdoctoral fellow. He got a very unique opportunity. He got the opportunity to point Webb for a full 2.5 days at a single galaxy. And this galaxy is the second most distant galaxy we know of. It's a unique opportunity because it is so bright, we can image this object very, very, very red. And we can see it in so-called visible light in the same way, in the same kind of light that our eyes see. And that's only because it's really bright, and it takes 2.5 full days of Webb pointing at a single galaxy. It's super expensive. But this is being led here at Penn State. And being able to see it in visible light lets us ask a few critical questions to understand the earliest stars and their black holes. And we can understand how many generations of stars lived in this object, just 290 million years after the Big Bang. Remember, sharks have been around for longer. And is there maybe an incredibly early supermassive black hole in an object like this? We'll find out soon. And Jake has a very special position, the Evolving Universe Postdoctoral Fellow. This is supported by Dr. Kiko Miwa Ross's very generous donation. So this is just a fantastic opportunity, I think, for astrophysics and for Penn State. I'm so excited about this. So that's where we are today. Little red dots. We might have solved the mystery, but it's posed even more fascinating questions about fundamental physics. These are early days. Webb has looked at less than 0.01% of the sky. There are far more mysteries waiting to be discovered in the deep universe. So stay tuned. More to come. And I'm going to end really soon here, but I just wanted to say one last thing. Imagine you had a vending machine, a cosmic vending machine. You dump in money, out comes facts about the universe. I'd probably use this one a lot. But how much money would you pay to know whether life exists on other planets by imaging their atmospheres and understanding the chemistry in them? That's something that we can do with Webb. To see the birth of the first stars, of the first black holes, and to map the universe out to the great impenetrable cosmic fog near the beginning of time, something we can't see past, not even with a telescope 10 times bigger than Webb. Okay, Webb is kind of it. We see to the edge of time with Webb. We can't go any farther, really. I want you to stop and think about a number. Well, was it $30? Well, I hope it was more. But to be clear, that's how much it cost you. The James Webb Space Telescope costs about $30 per American. And just to put that into context, this is a quote from one of my friends, Dr. Grant Tremblay. He's an astrophysicist at Harvard, but the James Webb Space Telescope is witnessing the birth of stars until the edge of time for what U.S. consumers spend annually on potato chips. And just to be clear, NASA Astrophysics is facing a 66% cut in 2026. This will be absolutely devastating for U.S. science, so this could easily all go away. That's all I wanted to say. Thank you all for coming. I'm going to leave up this final slide. How can you stay involved with some of the upcoming events here with Penn State Astronomy and Astrophysics? So thank you, and I'm very happy to take questions.
Thank you, Joel. There are a few questions in the chat. If I could just start with one. How far is the Webb from the sun? The Webb telescope.
Yeah, so I told you Webb is orbiting the sun. This is mostly true. This is more true than not, I think. Webb is about 1 million miles away from the Earth, and it's about 86 million miles away from the sun, same as the Earth. It's basically in the same orbit as the Earth. Webb is at a very special point in space, where the gravity of the sun and the Earth and the moon all cancel out, so it can just hang out there. It's a special place. But why did we put it so far away? It's pretty inconvenient, right? We'll never be able to fix it. Why would we do that? Well, it turns out we need to keep Webb super, super, super cold. And so Webb, as a telescope, is large, but it's surrounded by a much, much larger sun shield, which blocks out the sun, the Earth, and the moon, because any light from that would heat up the telescope so much we wouldn't be able to see anything but thermal glow from the telescope. So yeah, that's where it is. That's where it is relative to the sun, and no human has ever been out that far. So fingers crossed for it not breaking.
Perfect. What is the current state of Big Bang cosmology, which is now about 60 years old? What are the viable alternatives?
Yes. So the Big Bang is a very well tested scientific theory. It's been around for about 60 years. That is fantastic for my field. I mean, studying distant galaxies is much younger. It's more like 25 years old or something like this. So the Big Bang has withstood a number of very strong tests. That being said, there are some observations that don't really fit nicely into the Big Bang theory as we understand it, or more generally, the we call it lambda CDM, the cosmology of the universe, which starts out with a Big Bang, but then the evolution of the universe after the Big Bang is kind of governed by the kind of stuff that is in the universe. So there are some inconsistencies, something called the Hubble tension, where if you measure how fast the universe is expanding, it doesn't quite make sense. If you measure it in the very early universe and very late universe, these two numbers don't seem consistent with each other. So that kind of suggests the universe is growing differently than we expect. But there's no real belief that the Big Bang didn't happen from this, right? It's more like what kind of stuff in the universe existed after the Big Bang. And that's a big question. We actually don't know. So that's one big tension for the Big Bang theory or cosmology. The other tension well, one of the biggest components of the universe, something like 75% of the universe, is something called dark energy. And that's such a bizarre force that we only know a handful of observational facts about it, something like less than five. But it seems to work like a negative pressure. It pushes things away, dark energy. But we don't know what it is. We don't know how it works. We don't know how it evolves with time. We thought we had a sense for what it might be, something called the cosmological constant. But there is fresh news from one of the gigantic surveys here in the US designed to discover what dark energy is, that suggests dark energy is changing with time. It's actually getting weaker. And this is only a 3 sigma result. It's not confirmed. Something like 99.7% probably true, but we usually want a higher bar for science. If it were true, it would suggest dark energy is something called quintessence. A completely different thing, and it has completely different effects on the future of the universe. We're not doomed to a heat death, maybe, for one. But yeah, so to answer your question more directly, the Big Bang almost certainly happened. The real question remaining is what kind of stuff is in the universe, of which dark energy and dark matter are the biggest ones, and we still don't know what they are, but we're learning a lot.
Perfect. What's coming next after James Webb, and what will it allow astronomers to be able to accomplish?
Yeah, well, we have a few high-profile flagship missions coming up after James Webb. One of them, the Rubin Observatory, this is the largest camera ever built. This is on the ground, actually. But that has first light in just a couple of days on June 13th. This is a gargantuan camera pointed up at the sky. The camera itself is something like the size of a car. Um, and it's imaging the entire sky every 3 to 4 days. It's looking for things that go boom in the night and also trying to understand dark energy. So that's actually on the ground. It's a super exciting facility. Um, the next NASA mission to go up, the next big one, is something called the Roman Space Telescope. This actually, this is an old U.S. spy satellite, which I guess we built too many, and so they donated the spy satellite to the astronomical community something like 20 years ago. This is basically a Hubble-class telescope, built to look the other way. But we've repurposed it to look at the universe, and it's going to be a survey telescope. It's going to image large parts of the sky. And this is also, we're hoping it's going to tell us more about dark energy. It has a huge field of view. It can see thousands of distant galaxies at once. It can go very far, just like Hubble and Webb. And so the hope is this will be able to survey the universe, the observable universe, like a large fraction of the observable universe. Like this is, again, something we can only do once, cosmic cartography. We fill out the map and then we're done. Things like Roman and LSSC are going to do it. This is happening in the 2020s. It won't happen again. Roman is going to be awesome. I believe it's slated for launch in 2027. There is a fight over its existence right now in the presidential budget and the U.S. Congress. Roman has taken 20 years to come to fruition. Everyone's super excited about it. It may never be launched. It was well, it was originally cut in the budget this year, so it would just sit on the ground. And I think it's currently going back up, but it's not going to be finalized until the end of this year. That's the only NASA flagship mission we have scheduled, and with the huge cuts coming up, I don't see any more coming anytime soon. Nothing like Hubble and Webb or Roman. Fingers crossed for Roman and for the future of NASA astrophysics. It's a huge part of American leadership in science, and that shouldn't be taken lightly.
Perfect. That's great. We have a few more questions in the chat. If large black holes created during the Big Bang precipitated galaxies, could it be that black holes of all sizes were created but not large enough gravity wells to result in galaxies? Could this possibly be an explanation for dark matter?
Oh, that's a great question. Maybe. We certainly can't rule it out. Without knowing how they're created, it's hard to say the range of masses that they could have been created around them. If they are formed from the corpses of these very first stars, the first stars to light up the universe, we think those first stars are all pretty huge. The smallest ones being at least 10 times as massive as our sun, probably. We've never seen one. This is one of the holy grails of James Webb to find one of these mysterious first stars, and so we're still looking. But if that's the case, then that sets a lower bound on the masses of the first supermassive black holes, and they'd probably be, tens of masses of the sun. If they're formed from some exotic primordial physics right after the Big Bang, I have no idea. No idea. Maybe there are tons of little black holes. I can put a few limits on this. Very small black holes, they would actually evaporate through something called Hawking radiation. This is one of the things Stephen Hawking is famous for. And we'd see those kind of blowing up, very high energy events. So probably there's not a ton of those around, though it's very hard to rule out. Yeah, that could be there. We really just have to keep watching and keep learning to understand what physics might have formed these black holes and what kind of implications they might have. Black holes are probably not dark matter. We have a few experiments we've done that suggest that dark matter probably isn't in the form of black holes. It's circumstantial evidence, but it's pretty good. And so we can basically watch many, many, many stars at once and look for black holes passing in front of them. They should warp and distort the light and make them flash. And we don't see these flashes. There was a massive project monitoring for some 5, 6 years in the 90s, looking for this exact thing. seeing whether black holes, primordial or otherwise, could be dark matter. And in the Milky Way, at least, we saw not nearly enough of these flashes. We did see some, which is awesome. So we should have these wandering black holes around, but not nearly enough to explain dark matter. So probably not. But we don't know what dark matter is, so there may be surprises to come.
Perfect. How long, meaning length of time, is the communication back and forth between the James Webb for you to get information back and forth?
Yeah. So we have something called the Deep Space Network. Fantastic name. And these are gigantic radio telescopes. They're stationed all over the world. And they're pointed to communicate to our telescopes, our space shuttles, our satellites in deep space. And so they're all over the world so that we can stay in touch with these objects at any given time. When we launch a mission to the moon, James Webb has to briefly pause its upload so that we can talk to the astronauts or the satellites. The Deep Space Network is actually pretty overtaxed nowadays. We need more deep space communication devices. But that being said, James Webb is pretty close. It's something like 1 million miles away. So I don't recall the speed of light in miles, but I think that's less than a second, substantially less than a second for light to travel from us to the James Webb Space Telescope. Maybe a second, around there. Okay, so it's quite fast. There's very little delay.
Perfect. Is there any evidence that the laws of physics were different in the earlier years after the Big Bang? And additionally, was the life cycle of a star in the early days different than a new star forms today?
Fantastic question. This really cuts to the philosophy of science. There's no evidence that physics was different at early times. This is a question we ask every day. Because if we could change physics, we can explain a lot of our observations quite easily. And so there are tests for these things. People try to measure some evolution in time, some change, and say something like our fundamental constants. So the fine structure constant or other quantities that determine the laws of our universe. There's no evidence that physics changes with time. And so this is one of the fundamental assumptions that we make when we do cosmology and we understand galaxies in the early universe. And that assumption has been tested many times. And, there's no a priori reason the laws can't change very slowly with time. And we don't assume that's true necessarily, but we don't see any evidence for it. And so without evidence, we just say, hey, physics should work the same today as it did 13.7 billion years ago. That being said, our laws of physics do break down in some very small time scales, very high mass scales, at very high temperatures. So there are regimes where we know our laws of physics will, as we've written them down, they'll no longer hold. We haven't really been able to observe one of those regimes yet. Stars, it's a good question. Most stars should work mostly the same. Really the question is, all the physics are the same, but what are the stars made out of? The very first stars are the most interesting, maybe, because they don't have things like carbon, like nitrogen, like oxygen, these heavier elements. These heavier elements are critical to the functioning of stars like our sun. And so the way the sun produces light is by fusing helium atoms into heavier elements, helium and hydrogen and all these light elements. Hydrogen turns into helium, helium turns into heavier elements. But these heavier elements like carbon and nitrogen, they play a key role in that process. They're needed to catalyze fusion. The first generations of stars didn't have that. And so their formation and the way they did fusion, at least at first, has to be fundamentally different. Our best guess right now, having never observed one, the theoretical models are all over the place, but our best guess right now is that the first stars actually immediately forms things like nitrogen and carbon, and then use that to do fusion like we do in normal stars today. It's the best way to do it. But how these stars formed without any heavy elements, they form their primary coolants of the interstellar medium. It's how we disperse energy. It's how we get stars. Heavy elements throw energy out into space. And so the first stars are thought to be fundamentally different than today's stars because it was so hard to cool gas in the early universe without things like oxygen. So we think the first stars are probably way larger, way brighter, way bluer than something like our sun. Our best guess is that the first stars were more like a few hundred times the size of our sun and far, far, far brighter. And they may have had exotic deaths, as we've already discussed, directly forming things like supermassive black holes. Um, but just to be clear, this isn't because physics is different back then, at least not that we know of, but instead because they're made of different stuff, fundamentally different stuff, almost entirely hydrogen and helium, pristine.
Perfect. We have time for hopefully these two other questions. If these supermassive black holes were eating the gas around them, how were stars formed? Was there enough gas left over to form stars, or is she kind of misunderstanding that concept?
Right. Great question. So uh, it works like a giant, complicated, messy cosmic ecosystem, basically. But for gas to come close enough to the black hole to be sucked into the event horizon and to increase the mass of the black hole, it has to go through a whole series of processes to cool, to get close, to become dense, and then it'll start spinning around the black hole and it'll get superheated and hot and spin closer and closer and closer and then get right to the center. And then the black hole will actually eject most of the gas that comes in through these gigantic jets or these outflows. It'll spew it back into the galaxy. It's a very messy eater. And that's what makes these things so bright and energetic and incredible. Um, so, but stars also form from this gas that cools and gets close to the black hole. And so typically when we see a bright black hole, a bright supermassive black hole, it's associated with this gas that has cooled and come in and gotten close to the center, and then heated up again and got eaten by the black hole. But all of this is happening at once. It's a big old cosmic ecosystem. It's a jungle. All sorts of things are happening, and one of them is star formation. When gas cools and gets dense and falls into the center, it tends to form stars too. So we just tend to see black holes and star formation all happening at once. It's hard to have one without the other. And so I don't think you're misunderstanding anything. That's just how these systems tend to work, where we can see them. These first black holes apparently might be doing something else, though.
Perfect. Do we already have evidence that the supermassive black hole that can take a larger portion of its host galaxy than current galaxies, or is there still some data that can be interpreted in other ways? Okay.
Yes. Good. So great question. And I think this is a great one to wrap up here, is that that is our best guess right now. That we have this overmassive black hole. It's maybe 10% or 20% or 50% the mass of its host galaxy. And that means it grew way too early. But you've seen a lot of the data from the Webb telescope in this talk. They're just little red dots. They're a couple pixels wide, and we can see them at a few different wavelengths of light. We don't know that much about them. And so in order to get the masses of these galaxies and their black holes, we kind of have to assume they work like galaxies and black holes in the nearby universe, which is a reasonable assumption, but it could be wrong. It could be wrong by a factor of 10 or 50. That's astronomy. So this is our best guess. I think it's pretty good. I don't think it's wrong by more than a factor of 15. But if you told me we were off in their masses by a factor of 15, I might believe you. That would still leave us with supermassive black holes that are something like 10 to 100 times more massive than the Milky Ways. So that's astrophysics. Yeah, it would still be a stunning discovery, but there are large uncertainties, and we're working our best to understand what these are and get more data and do better science with it. So.